Hello everyone, my name is Liyanage Chamni Yasora and I am from the Department of Chemical Engineering and Green Energy Material and Process Lab. Today I will explain to you about my research based on lignin monomer production using flow-through pyrolysis and depolymerization of birch wood. This will be the content of my presentation. First of all, I will give you a brief introduction of my research and then I will explain to you about the experimental method followed by results and discussion and finally the conclusion. Today, alternative technologies are being developed to reduce our society's dependency on fossil resources. Several renewable resources such as hydro, solar, wind, hydrothermal and biomass can be applied to produce electricity or heat, but only biomass possesses a carbon precursor structure that is required to synthesize chemicals, materials and liquid transportable fuels. Biofuels are said to be carbon neutral because the carbon dioxide that is absorbed by the plants is equal to the carbon dioxide that is released when the fuel is burned. This means it doesn't release any extra carbon dioxide into the atmosphere. In this light, the concept of the biorefinery, in which biomass is converted to marketable products, is receiving a lot of attention. Lignocellulose, the most abundant type of biomass on Earth, is regarded as a highly promising feedstock. Though it is sustainable, exploitation should be closely managed. This is more realistic in the context of medium volume applications such as chemicals and materials. There are three main components in plant species. They are hemicellulose, cellulose and lignin, and they are present in 20 to 40, 40 to 50 and 20 to 30 percentages respectively in plant species. Lignin is the largest aromatic feedstock available on Earth. Lignin as a feedstock. Lignin has a three-dimensional amorphous polymer with a high molecular weight, and this polymer contains phenylpropane units which are formed from hydroxy and methoxy substituted phenylpropane units. The lignin polymer is primarily synthesized from three monolignols, p-coumaryl, coniferyl and cinephyl alcohol. They possess 0, 1 or 2 orthomethoxy groups respectively. Once incorporated in the lignin polymer chain, the corresponding phenolic units are denominated as p-hydroxyphenyl, guaiacol and syringil units. Depending on the type of biomass such as hardwood, softwood and grass, their composition of these three monolignols can be varied. There are different types of CC bonds such as beta-beta, beta-O5 and ether bonds present in lignin. With a relative contribution of 50 to 80%, the beta-O4 ether bond is by far the most abundant interunit linkage in lignin. The objective of any biorefinery is the conversion of biomass into a spectrum of marketable products. Due to the heterogeneous and complex nature of the lignocellulose matrix, a fractionation strategy is often applied prior to tailored processing of each individual product stream. Lignocellulose is processed under harsh conditions to separate the carbohydrates from lignin, causing irreversible chemical alterations in lignin chemical structure. The resulting lignin side stream has long been considered a waste product and is mostly burned for process heat and electricity. The most common fractionation methods can be divided into two main categories: base catalyzed fractionation and acid catalyzed fractionation. Kraft pulping, sulfite pulping, and soda pulping are the most common base catalyzed fractionation methods used in the industry, while concentrated acid hydrolysis, dilute acid hydrolysis can be considered under acid catalyzed fractionation. Are traditional lignin streams a promising feedstock to produce chemicals? Obviously, the production of chemicals through lignin depolymerization is greatly influenced by the properties of the lignin substrate. Analysis of isolated lignins, therefore, embodies an important feedback mechanism that enables the optimization of existing fractionation methods. Aryl ethers, mainly represented by beta-O4 bonds, are the dominant interunit linkages in native lignin as mentioned previously, but their abundance decreases significantly during most fractionation processes. Unfortunately, a reduced beta-O4 content in the isolated lignin is typically linked to an impaired lignin reactivity and a lower phenolic monomer yield under lignin depolymerization. Depolymerization of native lignin to stable monomers. Compared to most isolated lignins, the native lignin structure is more susceptible to depolymerization as a result of its higher ether bond content and reduced degree of CC cross-linking. A valid strategy therefore is to isolate lignin from lignocellulose feedstocks with a minimal alteration of its original chemical structural features. This way, the obtained lignin isolate forms a more reactive substrate for further conversions to chemicals. Despite lignin's strong tendency towards condensation, several fractionation methods have achieved the isolation of native-like lignin, especially with respect to the preservation of beta-O4 bonds. To favor lignin isolation over lignin condensation, most of these innovative methods apply mild process conditions, for example by improving the lignin solvating power of the reaction medium. Alternatively, active stabilization mechanisms were introduced recently, allowing a higher process severity and higher isolation yields of native-like lignin. Reductive catalytic fractionation, or RCF, is a biorefinery approach that integrates biomass fractionation or delignification with lignin depolymerization stabilization, the latter being enabled by the redox active catalyst. Unlike more traditional fractionation approaches such as Kraft pulping, RCF yields an uncondensed, low molecular weight lignin oil comprising phenolic monomers in close theoretical yields. How does RCF work? The most essential ingredients to operate an RCF biorefinery are lignocellulosic biomass, an alcohol or cyclic ether solvent, a heterogeneous redox active catalyst. Often water is used as co-solvent. These are typically added to a high-pressure batch reactor which is heated to 180 to 250 for 2 to 8 hours. Heating induces solvolitic extraction of lignin from the biomass. Flow-through reactor setup for the reductive catalytic fractionation. Most RCF studies up to date have been conducted in batch, but a flow-based process enables the acquisition of intrinsic kinetic and mechanistic data essential to accelerate the design, optimization, and scale-up of RCF processes. There are many advantages of a flow-through reactor setup that is being used for RCF. A flow process enables acquisition of intrinsic kinetic and mechanistic data essential to accelerate the design, optimization, and scale-up of RCF process. And also, easy separation of the carbohydrate-rich pulp without the mixing with the catalyst can also be obtained. But one of the main disadvantages of a flow-through reactor setup is the high solvent consumption. Now I will explain to you the experimental method that I use during this study. You can see the experimental reactor setup in this slide. In here, 5 grams of birchwood is first sololysed in the presence of methanol at a temperature of 250 degrees Celsius and at 100 bar pressure. Then the sololysed liquor obtained is again depolymerized in the presence of 30 bar hydrogen pressure and PD carbon catalyst bed. Then the product mixture is first vacuum filtered to separate the catalyst from the liquid mixture. Then it is rotary evaporated to remove the methanol and the liquid and then liquid extracted for 3 times using dichloromethane. Again it is rotary evaporated to remove the dichloromethane, and finally the bio-oil is obtained. After the product purification, the final bio-oil will be analyzed using gas chromatography, time of flight mass spectroscopy, and gas chromatography flame ionization detectors to calculate the monomer yield with respect to the lignin weight present in the initial birchwood used. In the first spectra, you can see the GC of MS chromatogram that I obtained for the final bio-oil and the gel permeation chromatogram to see the molecular weight distribution of the obtained bio-oil. Now I will move on to the final part of the presentation, the conclusion. Flow-through reactor setup is established to facilitate the reductive catalytic fractionation of the birchwood. Flow-through RCF of birchwood over PD carbon resulted in near theoretical monomer yield, degree of delignification, and holocellulose retention of 49%, 81%, and 90% respectively at 250 Celsius, and initial hydrogen pressure of 3 megapascal and a reaction time of 3 hours. These results are comparable to the results obtained from batch reactor studies done up to now. Monomer yield achieved is the highest value achieved from the continuous reactor studies conducted so far. Holocellulose retention is 90%, which is higher than the value obtained from batch reactors due to the easy separation of residual biomass pulp from the catalyst during a flow reactor. Thank you everyone.